Let us now look at another intuition of the derivative of a function at a point C. We know that the derivative of a function at point C is defined as limit x tends to c of f of x minus f of c divided by x minus c. So let us look at the graph of a function. I have taken one function and let us just explore what happens for this function. So I have already plotted the point C. Suppose we take a point x. Okay, so the corresponding point f of x would be somewhere here. So this is the f of x. So this is f of x. This is f of c. Okay, so f of x minus f of c is this quantity. X minus c is this length. So f of x, so if you look at this in this triangle, this is x minus c and this is f of x minus f of c. So the quantity f of x minus f of c is the slope of this line. Okay. Now, what am I doing? I am taking x closer and closer to c. So suppose if I took a different x now. Let's say I took another x dash. Okay. So corresponding to x dash, I get the point here and I get a point here. So my x dash minus c is equal to this quantity and f of x minus c is equal to this quantity, this length. Okay. So this is equal to f of x dash minus f of c. Alternatively, we can say that this is x minus c and this is equal to f of x minus f of c. So f of x dash minus f of c is the slope of this line. Such a line connecting two different points on the curve is called a secant. Now for each x, you get a secant line connecting x comma f of x and c comma f of c. As x tends to c, and notice that we are interested only in the slope of this line. So as x tends to c, you get different slopes and these slopes converge to some value. So if you draw a line of slope this limit through the point c of comma f of c, we get a tangent to the graph of the function. Now I don't know how many of you are familiar with the notion of a tangent, but I'm sure you have at least seen tangents for circles. It is actually kind of difficult to rigorously define tangents to a general curve, but in fact one of the ways of defining it rigorously would be through derivatives. But because we are familiar with tangents to circles, we all kind of have an intuitive understanding of tangents. And we are just carrying over that intuition. So do not take it too seriously. But this still helps us because most of the cases, if we see a graph, we see a curve, we know what the tangent to that curve is at a point. So, and that is all I want you to understand at this point. Using this intuition, it is now pretty easy to see why the derivative of mod x at the point 0 does not exist. So if you take any point c that is less than 0, we see that the tangent to the curve or the graph of the function at this point c comma f of c is nothing but this line itself. Correct? And that has slope minus 1. So that is why f dash of c is minus 1 if c is less than 0. Remember, we had seen this. Similarly, if we take a c that is greater than 0, then clearly the tangent to the curve passing through that point c comma f of c is nothing but this line. And again, the slope of this line is equal to plus 1. That is why the derivative f dash of c is equal to plus 1 if c is greater than 0. Now if we take the point 0, we do not know which tangent to take. What is the tangent? Is this the tangent or is this the tangent? That's confusing, right? As this confusion exists, we will not be able to find a tangent to the curve at the point x equal to 0. And that is why we say that the function is not differentiable at the point 0. So intuitively, why is mod x not differentiable at 0? It is not differentiable at 0 because we cannot find a tangent line at that point.